Welcome to BKW Physics. I'm Mr. McConnelly. And last time we talked about radioactive decay, and we're going to start there as a launching point. When you have radioactive decay and the nucleus is trying to find its stable configuration, it's giving off particles, the mass-energy relationship is still conserved. And what that relates to is it relates to Einstein's theory of special relativity. He wrote the highly recognized but poorly understood equation E equals mc squared. In its very most basic sense, it just says energy in joules is equal to mass in kilograms times the speed of light, 3e8, all squared. So he said if you take the speed of light, treat it like a constant, you square it, you times it by the mass, it will tell you how much equivalent energy you have. That's what the equation does for you. So if you have mass, you have energy, and if you have energy, you have mass. Now, they're not equal numbers, don't get me wrong here, but one you can convert and figure out how much of the other you have. Now, a lot of people can think of it like this. They can think of, yeah, if I got a chunk of firewood, I got a mass there, and if I burn it, I get energy. So they can see it going this way, and in their mind it seems to work. But if I say you have, a fire, can you think of that in terms of it being mass? That's a little more awkward. So what we're going to do today is we're going to show one application of this, and then in other subsequent lessons we'll come back to this idea and add more information so you have a fuller picture. So let me start with a real quick example of E equals mc squared, and then I'll get into a more in-depth example. Two examples here. This first one here. What if I wanted to know the energy in one atomic mass unit, one AMU, atomic mass unit. By the way, remember atomic mass unit? Usually we're referring to, one atomic mass unit is usually one neutron. So if we take E equals mc squared, and we plug in the mass, the rest mass of one neutron, which I looked up to be 1.66 E negative 27 kilograms. Very small mass. And I times it by the speed of light squared. This is a pretty awkward big numbers, but when I work this out, it actually gives me a 1.49 E negative 10 joules of energy. So it's saying one neutron is equivalent to that much energy, which is not much, it's negative 10. Okay, so this is a very small number, but a neutron has a certain measurable amount of energy associated with it. But what the physics reference table does is a lot of times it gives these energies in electron volts, as we talked about the other day when we did the energy level diagrams. So why don't we convert this number into electron volt, because I got something else I'm going to point out to you here. If we take 1.49 E negative 10 joules, and we convert it into electron volts, remembering that 1.6 E negative 19 joules is 1 electron volt, so if I divide, I'm going to get a number that is 9.31 E8 electron volts. But that's the way I would write it. That's not the way the reference table writes it. Unfortunately, the reference table writes it this way. It's awkward a little bit. It's 9.31 E2 mega electron volts. That is the way it's written in the reference table. And if you could please find that right now on your reference table, it's on the front page. Also, while you're on that front page, page, note that in the first box on the front page, the rest mass of a neutron, I guess they write it as 1.67, but that's where I got the number from. And then if you move, let's see, 1, 2, 3, 4 boxes up from the bottom, it says 1 universal mass unit, 1 AMU, is equal to that amount of energy. And that's good because now we can say, okay, if you got 3 neutrons, you can just multiply this number by 3. You don't have to go through all the work that we went through to get there. Okay, it's kind of a shortcut. So that's the first thing. Shows you a basic application. Next, definitely a little bit more in depth, and I need some space, so I'm going to erase what I have on my board. If you take this example here and work through it with me, if we take nitrogen, 15,7 nitrogen, if you read a little bit about chemistry, what you'll remember is that means you have 7 protons and 8 neutrons. That's what that notation means. Protons are usually written as a hydrogen, so you have 7 of these 1,1 hydrogens. And neutrons, we usually just use the notation 1/0 with a lowercase n. Okay? Now, I will tell you that, do it in different colors, so it doesn't get too confusing. I will tell you that each proton in atomic mass units has a mass of 1.0078 U, is the abbreviation for atomic mass units. And I will tell you that neutrons have a 1.0087 U. So that one says 78, that one says 87. They're not the same number. So now if I do a little math here, if I say, okay, well, I have 7 of these protons, so 7 times that number would give me 7.0546 U. And if I have 8 of the neutrons, that would give me 8.0696 U. And I add that up, what should it give me? Going back to the beginning, it should give me 15. Okay, it should give me 15 because these are the pieces that make up the whole. So when you add this, it should give you 15. I think most of you are smart enough to see it's not going to give me exactly 15. I got all this extra change here. This already gives me 15 by itself. It's going to give me 15.1242. Huh. Doesn't add up to exactly 15. Now, this concept I'm going to address in more detail at a later time, but for today I want it to suffice to say what holds a nucleus together, that energy that holds a nucleus together is equivalent to mass. Okay? Or another way to say it is the binding energy is equivalent to a mass defect. This right here is some mass defect. And it would be equal to the binding energy. The mass defect is equal to the binding energy. So, if I take, let's figure out how much binding energy this really is. That should be easy. So if I take the 0.1242 part of it, the leftover part of it there, I can use my handy-dandy conversion that we just saw a moment ago, where 1 AMU was equal to 9.31 E2 mega electron volts. That was the conversion we just came up with. And when I multiply multiply this out, it is going to tell me that in fact I have 115 megaelectronvolts of energy. So what's this called again? This is called the binding energy. So we have binding energy and we have mass defect. And because of Einstein's E equals mc squared, they're equivalent. Okay? It goes something like this. It goes something like this. If you have nitrogen by itself, and you just weigh the whole nucleus as a chunk, the number you're going to come up with is a 15.001. It's not exactly 15, but it's real close. Okay? So if you weigh it as a chunk, you take the whole nucleus, boom, you weigh it 15.001. When I take all the individual pieces, it doesn't add up to that. You can see it's a tenth of an atomic mass unit at least larger. They're not equivalent because when you start taking the individual pieces apart, it takes some work. You're tearing the pieces apart because what's holding them is binding energy, and therefore that's equivalent to mass. Okay, so as you start to tear them apart, you're like gaining mass in the process. And you're going to see this play out in a much more large scale. This is a small scale example here. When we do it with fission, you're going to see the numbers, because numbers for uranium are really big nucleuses. This is a tiny one, this is a 15. You get up to a 238, and you can imagine that this binding energy is not going to be a tenth anymore, it's going to be a pretty big number. And that's going to eventually play out so you can understand why nuclear power plants and nuclear fission and fusion create so much energy. Because you're taking your mass defect and you're turning it into energy, raw, unadulterated energy, and you get a lot of it. So for today, physics.